Hey guys, welcome to PDV Leadex Education. Today we are going to be demystifying organic chemistry advanced level June, or we are going to be demystifying advanced level chemistry paper 2 June 2022, and we are going to answer some particular questions in the question paper. So get seated and let's do this all together. So as you can find on the board is a synthetic route, which was question 5. And before that, I would like to mention that I understand that organic chemistry is in fact your worst section of advanced level chemistry, right? Or maybe not you, but in general, organic chemistry disturbs so many of the students out there, and we just want to tell you that with PDV Leadex Education, organic chemistry is going to be without stress. So get seated and let's do this all together. You should see how organic chemistry flows, or how organic chemistry is going to start flowing in your blood as from today. Okay, so here we have a synthetic route, and the question says that study the reaction scheme below and answer the questions which follow. Okay, so how do we study the reaction scheme? Right, that's our reaction scheme. Before you tackle such questions in the exam, right, the first thing you must do is to identify the different homologous series involved. So what are homologous series? Homologous series here we are referring to alkanes, alkynes, alcohols, aldehydes, or carbonyl, or aldehydes, ketones, carboxylic acids, nitrates, acid chlorides, and all the rest, right? That's what you mean by homologous series. So you must begin by identifying to which homologous series each of these compounds belongs. Once you do that, it will be much easier to know now the different reagents and reaction conditions involved in the different conversions. So let's get to that. Now, before that again, to identify each homologous series, you will need to know the general molecular formula of the different homologous series in organic chemistry. You need to know how the compounds of each homologous series are written, because with that it will be much easier to identify the homologous series. Okay, let's see how we do that. Now, compound A has only carbon and hydrogen. So compound A must be a hydrocarbon. It must be a hydrocarbon. And hydrocarbons are of 3 different types. We have the alkenes, the alkynes, and the alkenes. We have the alkenes, and the alkynes. So which one is compound A then? We look at the formula. We have CnH2n plus 2, C3H8, that's 2n plus 2. So compound A is an alkane, right? So compound A here is an alkane. Now, looking again, we identify compound E. Compound E equally has only carbon and hydrogen. So compound E also is a hydrocarbon. Now, is it alkane, or alkyne? We look at the formula. C3H6, CnH2n. So compound E is an alkene. So here we have an alkene. Now, let's get to compound B. Compound B, we have a halogen attached to an alkyl group. Halogen to alkyl group, we call them halogenoalkanes. So compound B is a halogenoalkane, and they are written as RX. Compound F also has a halogen attached to an alkyl group. So compound F equally is a halogenoalkane. Then compound C. Look at when you look at C, what do you notice? That there is a nitrogen atom, right? There is a nitrogen atom in compound C, and that the bromine has left, right? The bromine has left, or the bromine has been replaced. But before that, generally when you have only carbon, hydrogen, and nitrogen, when you have only carbon, hydrogen, and nitrogen in a compound, then the main probability is that compound is a nitrile, right? That compound is a nitrile. right? Nitrates are written as RCN, RCN, where R is an alkyl group. Now, but for the compound to be a nitrile, there must be an increase in the carbon chain. The number of carbon atoms must increase by 1 from the previous compound. Why? Because nitrates are formed, right, from the nucleophile C, from the cyanide ion, which is a nucleophile. Nitrates are formed from the cyanide ion, or by attack of the cyanide ion. So when this ion substitutes an atom, right, it brings an extra carbon. So that's why the number of carbon atom increases by 1. So let's verify if it actually increases by 1. How many carbon atoms are in B? 1, 2, 3. There are 3 of them. How many are in C? 4 of them. So carbon atoms number has increased by 1. So compound B, compound C actually is a nitrile. So here we have a nitrile. And what's compound D? Compound D, the main peculiarity there is that it has 2 oxygen atoms. 2 oxygen atoms. In organic chemistry, there are just 2 homologous series that generally have 2 oxygen atoms. Those are the carboxylic acid and the esters. The carboxylic acid and esters. Carboxylic acids are ROOH. Esters are ROOR'. Both of them have 2 oxygen atoms. So whenever you see a compound that has O2, then think of that compound being a carboxylic acid or an ester, right? So those are the general cases. Now, carboxylic acids are written as CnH2nO2, CnH2nO2, and there clearly we have CnH2nO2. So compound D therefore is a carboxylic acid. Compound D is a carboxylic acid. So there we have identified each homologous series. The next thing for us will be to identify the reagents and the reaction conditions. The reagents and the reaction conditions. So let's quickly do that. Compound A is an alkane. We are leaving from alkane to haloalkane. Alkane to haloalkane. We know that alkanes are saturated, and alkanes undergo just one type of reaction, which we call free radical substitution reaction. Free radical substitution reaction. And in this reaction, in this free radical substitution reaction of alkanes, we have UV light, right, which provides the energy for the formation of the free radicals. So a free radical generally is formed from a halogen. So what halogen are we adding? We are adding bromine, right? We are adding bromine. So our reagent is bromine. And what's the condition? UV light. UV light provides the energy for the formation of the free radicals. So that is the reagent and the condition for the first step for Roman 1, to leave from propane, this is propane, to bromopropane. So here we have propane to bromopropane. Now, Roman 2, we are leaving from haloalkane to nitrile. We know that the haloalkanes equally are saturated, but thanks to the high electronegativity of the halogen, right, the carbon halogen bond is highly polarized. Once this bond is polarized, it creates a positive carbon center. This positive center is easily attacked by nucleophiles. Nucleophiles have electrons, so they come here to donate electrons and form a covalent bond, right? So haloalkanes undergo nucleophilic substitution reaction. Once a nucleophile comes, right? Once a nucleophile comes, it substitutes the halogen, and you have this, right? You have that. So haloalkanes undergo nucleophilic substitution reactions. But depending on the reaction conditions, haloalkane can also undergo elimination reaction, right? They can also undergo elimination reaction in which they produce alkenes. So here we have haloalkane to alkene. So this one here is elimination reaction. We have haloalkane to a nitrile. That one is nucleophilic substitution reaction. So what is the nucleophile? The nucleophile there is the cyanide ion. But where does it come from? It comes from potassium cyanide or sodium cyanide, right, in ethanol. So our reagent for Roman 2 is potassium cyanide or sodium cyanide in ethanol, right, or potassium cyanide or sodium cyanide and ethanol. Condition under reflux, right? All the reactions of haloalkanes take place under reflux. All the reactions take place under reflux. Now we get to Roman 3. Roman 3, we are leaving from a nitrile to a carboxylic acid. That process is called acid catalyzed hydrolysis. Or before that, how can you easily see that? Right? How can we easily see that on the hood? Now, what do you look at? Look at something here. We are leaving from the nitrile to a carboxylic acid, right? So if you observe this, what do you notice? That we have just replaced nitrogen with what? With this. And what is this? This is no, not water, not water. We have replaced that by that. So this one actually comes from water, right? From water and an acid. So leaving from a nitrile to a carboxylic acid, the process is called acid catalyzed hydrolysis. Acid catalyzed hydrolysis, and the process takes place under reflux. So what do we need for Roman 3 as reagent? We need water and dilute hydrochloric acid. Water and dilute hydrochloric acid. The acid catalyzes the hydrolysis of the nitrile into the carboxylic acid. And what's the condition under reflux? We come to Roman 4. Roman 4, we are leaving haloalkane to alkene. As we earlier mentioned, haloalkanes also give alkenes by a process called elimination reaction. Elimination reaction, because we are leaving from what? A compound which is saturated to a compound which is not saturated or which is unsaturated. That means that a double bond is formed. So the process is called elimination reaction. And this reaction actually depends on whether the haloalkanes undergo elimination or substitution or nucleophilic substitution. It all depends on the reaction conditions. So what happens is that we are going to react the haloalkane, right? We are going to react the haloalkane with sodium hydroxide. That's any alkali. Now, if we do that in the presence of water, then we are going to have an alcohol. If we do it in the presence of water, we have an alcohol which is by nucleophilic substitution. But if we do it in an alcohol, right? If we do it in an alcohol as solvent, then we are going to have an alkene in what we call elimination reaction. So haloalkanes react with sodium hydroxide to either give alcohols or alkenes. Nucleophilic substitution or elimination reaction. It all depends on the reaction condition or the reagent that you use. So if you use the base or the alkali in water, you have an alcohol. If you use the alkali in an alcohol, then you have an alkene. So for Roman 4, our reagent is sodium hydroxide in ethanol. Sodium hydroxide in ethanol, and the condition there is under reflux. Lastly, Roman 5, we are leaving from alkene to haloalkane. Alkenes to haloalkane, unsaturated to saturated. We call that addition reaction, right? Here we have addition reaction. The alkenes have a double bond. The double bond is an electron-rich center. It has pi electrons. So this double bond will easily be attacked by electrophiles, right? The double bond will easily be attacked by electrophiles. So the mechanism there is called electrophilic addition. Electrophilic addition, right? Because the attacking reagent is an electrophile. Why an electrophile? Because the compound has an electron-rich center. So what are we adding? Let's look at bromine is added, and again hydrogen H6 H7, one hydrogen has added, which means that we are adding what? Hydrogen bromide. So our reagent for Roman 5 is hydrogen bromide, right? The alkene is prob 1 in. The alkene is prob 1 in, and prob 1 in is not symmetrical. So this mechanism is going to follow Markovnikov addition, because the alkene is unsymmetrical and hydrogen bromide is also unsymmetrical. So for Roman 5 we shall have electrophilic addition reaction by Markovnikov's rule. So reagent hydrogen bromide, condition room temperature or 20 degrees Celsius. Take care, all electrophilic additions of alkenes take place at room temperature or 20 degrees Celsius. Okay guys, there we have completely demystified the synthetic routes, and we are going to have a little break. If you do not understand anything, just get back, just listen, get again through the video till you understand it. So after the little break, we are going to come back and continue to answer the questions. So see you in a little while. And before I forget, I do believe that you enjoyed the lesson, so please kindly like the video, share the video with your friends so that others can also come and enjoy organic chemistry with PDV Leadex Education. Please kindly do me the favor and share the video. Thank you and see you.